Hi and welcome back to part 5 of Neurons. What we want to look at now is the actual action potential. So look at this phenomenal picture of a cell body underneath, this big sort of balloon underneath here is a cell body. And all these little nubs here are dendrites of a different cell there that are connecting to that particular cell. So very remarkable that one neuron alone will have so many different connections. So we want to understand that nerve impulse. We want to understand how that travels. And it's called an action potential. And what it really is a change in charge. So we're thinking of charges, positive charges, negative charges, what's happening with those charges. And they kind of travel as a wave along the membrane of the neuron and along the axon, really more specifically. So it's like current, it's like electricity. So these neurons that you have are just sending electricity signals over to a gland to secrete something, or over to a muscle to contract something. So these signals are electrical. So look at what's going on here. This is animated. Take a minute to see. It starts out negative in the inside, and then it receives a signal and it starts to flip and flip and flip and flip, and all of a sudden it flips back, right? So it's going to be negative now on the outside, negative, flip back, flip. This little flip thing that's happening are signals that are traveling along this axon as long as there is incoming signal from over here. So if you're having someone touch you on the arm, right, those signals are going to continue to come, and this electricity is going to continue to travel like this. And then if you stop these here, then we're going to go back to what we call a resting potential. An action potential is when that incoming signal on the dendrites is traveling down an axon to the other end. So let's first start by looking at one that doesn't do that, a resting neuron. So a resting neuron, like the picture down below here, is going to have this uneven distribution of ions, and they're going to be more of the negative ones inside and more of the positive ones on the outside. So these ions, I mean, you know this before you take a class like this one, because you do things like take electrolytes, right? If you're going to go for a long hike or a long run, electrolytes are ions. It's charges. And you know that when you sweat out a lot, you're going to lose some of these, so you have to replace them. So think of those. Think of those ions or those electrolytes that are in your body, and those are the ones, they're like little batteries. That's why I put the picture here. They're little batteries that are functioning. So how does that battery work? Well, inside the cell or inside the axon are these negative charges, and they're there when it's resting. And we have such a large accumulation of sodium on the outside, it's going to be very positive on the outside of the cell relative to the inside. And the inside, even though it has these positive potassium ions, is still going to be very negative. And the reason it's very negative is because of large proteins inside the cell that are negative. So these proteins are going to give us that negative charge on the inside in comparison to the outside. Now, let's look at the specifics. Sodium ions are in large concentrations along the outside of the cell membrane. Okay, very positive on the outside. Potassium ions are in a large concentration along the inside of the cell membrane. Now, the trick is that potassium is also positive. So how is it that the inside of the cell is predominantly negative? Well, it's because of these proteins. You have to remember those at all times. So even though both of these ions are the same charge, there's going to be something else that sort of disrupts that charge, and it's those proteins. So there it is, more negative inside, more positive outside. Potassium's in, sodium's out. And that is a little chunk that you're looking at there, right from, directly from an axon here. Okay, what happens next? We're going to now start a neuron impulse. It was resting, and now we're going to begin an action potential. So what does it need? How does that start? Well, it would require a stimulus. And that stimulus needs to be not a little weak, wimpy stimulus. It needs to be a stimulus that's sufficient to actually reach something that we call threshold. So if someone takes a magazine and swats you on the arm, you're going to feel it. If a mosquito lands on your arm, you might not. So that might be a stimulus of inadequate strength. It might not be strong enough for you to detect it. But let's say it is a magazine across your arm, okay? There was a mosquito on your arm and someone comes to swat it and you feel that swatting, okay? So that membrane we're saying is irritable, and you're going to feel that magazine landing as you swatted that mosquito on it that you never felt. You never felt the mosquito, but you felt that magazine as someone tries to swat it off you. The magazine was above threshold. The mosquito was below threshold. You never felt it. So what happens? You get swatted, right, with a magazine, and there is a change in the permeability of the membrane to sodium. What does that mean? It means that ordinarily sodium is happy on the outside of the cell and potassium is happy in the inside of the cell, and they're sort of staying in that area. Why? Because those channels that allow the passage of these ions are closed and they're not allowing the passage. But once you get a stimulus, then those channels can open and there is a change in that permeability, meaning sodium that used to happily only be on the outside of the cell is now able to flow into the cell through a channel that opened because you got swatted with a magazine. And it happens in order. First, the sodium does its thing and flows into the inside. It does so because there's many more sodiums outside than in, and that is just a concentration gradient. Anything that's more concentrated in one area tends to want to move to the other area if you allow it. Potassium is the same. It's in high concentration inside the cell, and if you were to open the potassium channel, it's like opening a gate. It would flow out. So you have this flipping of charges, and the result is that you create current. That's what an action potential is. So if we want to look at it more specifically, we're going to give it names. The first name we're going to give it is depolarization. You had these poles. You had this pole that inside was negative and outside was positive. That's like a pole. One end is one thing, the other end is the other. But you're going to undo that. You're going to depolarize that, undo it. And then you're going to allow, as it shows in this picture, sodium that used to be only on the outside to come in. And it's going to come in. And if I bring in enough of those positive ions, then does it make sense to you that I would end up with so many of them that it is no longer negative inside the cell, but rather positive? So it's that allowing of those sodiums to enter. How did you allow them to enter? There was a stimulus. What was the stimulus? The magazine hitting your arm. And what did that do? It opened channels. And what did that do? Sodium flow was able to flow inside the cell and create an action potential. Okay, so far so good. The only thing that changed was sodium came in. Then what? This is just an enlargement of that one slide so that you can see it bigger, especially when it's printed. Well, what's going to happen next is, in order, first sodium, and then just because of that magazine also, there are these slowpoke channels that are the potassium channels. They're going to take a little longer. They too are going to decide to open. And if they decide to open, potassium, there was much more potassium inside the cell than out. So you take that magazine to your arm, and in time, the potassium channel opens, and potassium channels rush out of the neuron. So step one, sodium came in. Step two, potassium goes out. And what that does is that it repolarizes the membrane. It goes back to what it used to be because we flipped. We brought one in and took another one out. So it actually returns back to its initial state. Repolarization. Now things are a mess because we have too many potassium ions out and too many sodium in, and we have to fix it. We have to kind of put Humpty Dumpty back together again and return the potassium ions to the inside and return the sodium ions to the outside. And the way we do that is with a different channel. It's called the sodium-potassium pump. And that is going to say, okay, sodium, you go back out, potassium, you come back in. Sodium, you go back out, potassium, you come back in. And we bring it back to the original configuration. With illustrations here, this is a sodium channel in blue, a potassium channel in green, and the sodium-potassium pump. So you would first have step 1, sodium is allowed in, right? And then the next step is that this would open up and potassium would go back out. And then we have a mess because we have too many potassium out and too many sodium in, so we have to fix it. And the sodium-potassium pump then is going to do what? It's going to take the sodiums and put it out, and take the potassium and bring it back in. Okay, so it does it for every 3. The interesting thing is that for every 3 sodiums that come in, that go out, 2 potassiums come in. And this shifting, come in, go out, fix, come in, go out, and fix, that is what an action potential is. Nerve impulses are propagated in one direction only, and that's because it takes a minute to fix what you already undid, and that fixing takes a while, so it won't propagate in the opposite direction. So it is a one-way movement along the axon, away from the cell body. What happens when it reaches the other end? So it travels, that electricity, and it reaches the very terminal end here. It's going to now send a signal to the next cell. But it can't just shock the next cell. This electric shock can't say, okay, I shock you and now you do the same thing. It actually needs an added step in between, and that is a chemical step. So I'm going to stop this now and leave just a very few slides for the last recording. Thanks.